Data structures for graphs. There are several possible ways to represent graphs. We discuss 4 useful representations here. We assume the graph G is equal to V, E contains n vertices and m edges. Let us look at adjacency matrix. We can represent G using an n by n matrix M where element Mij is, say, 1 if I, j is an edge of G and 0 if it isn't. This allows fast answers to the question, is I, j in G, and rapid updates for edge insertion and deletion. It may use excessive space for graphs with many vertices and relatively few edges, however. Consider a graph which represents the street map of Manhattan in New York City. Every junction of 2 streets will be a vertex of the graph with neighboring junctions connected by edges. How big is this graph? Manhattan is basically a grid of 15 avenues, which crossing roughly 200 streets. This gives us about 3000 vertices and 6000 edges, since each vertex neighbors 4 other vertices and each edge is shared between 2 vertices. Such a small amount of data should easily and efficiently stored, but the adjacency matrix will have 3000 into 3000, which is 9 million cells, almost all of them empty. Adjacency matrix for this graph is represented in the form of this matrix. Adjacency lists. We can more efficiently represent sparse graphs by using linked lists to store the neighbors adjacent to each vertex. Adjacency lists require pointers but are not frightening once you have experience with linked structures. Adjacency lists make it harder to ask whether a given edge I, j is in G, since we have to search through the appropriate list to find the edge. However, it is often surprisingly easy to design graph algorithms which avoid any need for such queries. Typically, we sweep through all the edges of the graph in one pass via a breadth first or depth first traversal and update the implications of the current edge as we visit it. Adjacency lists in matrices. Adjacency lists can also be embedded in matrices, thus eliminating the need for pointers. We can represent a list in an array, or equivalently, a row of a matrix, by keeping a count k of how many elements there are and packing them into the first k elements of the array. Now, we can visit the elements from the first to last just like a list, but by incrementing an index in a loop instead of cruising through pointers. Adjacency list in matrix for this graph is as shown in the figure. This data structure looks like it combines the worst properties of adjacency matrices, large space, with the worst properties of adjacency lists, the need to search for edges. However, there is a method to its madness. First, it is the simplest data structure to program, particularly for static graphs which do not change after they are built. Second, the space problem can in principle be eliminated by allocating the rows for each vertex dynamically and making them exactly the right size. To prove our point, we will use this representation in all our examples. This is the code for reading in a graph from a file. So read underscore graph, it takes an input graph G, pointer to the graph G, boolean directed. So int I is a counter, m is the number of edges, x, y are the vertices in edge x, y. So we initialize graph G, then read in the vertices, loop over for I is equal to 1, I less than or equal to m, I plus plus, read in x and y. Then call the function insert edge g x y directed. Initialize graph G. So again, I is the counter, g of n vertices is equal to 0, g of n edges is equal to 0. For I is equal to 1, I less than or equal to max v, I plus plus, g degree of I, degree I is equal to 0. Table of edges. An even simpler data structure is just to maintain an array or linked list of the edges. This is not as flexible as the other data structures at answering who is adjacent to vertex x, but it works just fine for certain simple procedures like Kruskal's minimum spanning tree algorithm. As we have seen before, we will use adjacency lists in matrices as a basic data structure to represent graphs. It is not complicated to convert these routines to honest pointer-based adjacency lists. We represent a graph using the following data type. For each graph, we keep count of the number of vertices and assign each vertex a unique number from 1 to n vertices. We represent the edges in a max v into max degree array, so each vertex can be adjacent to max degree others. By defining max degree to be max v, we can represent any simple graph, but this is wasteful of space for low degree graphs. We represent a directed edge x, y by the integer y in x adjacency list, which is located in the subarray graph edges x. The degree field counts the number of meaningful entries for the given vertex. An undirected edge x, y appears twice in any adjacency based graph structure, once as y in x list and once as x and y's list. To demonstrate the use of this data structure, you can see the previous reading from a graph algorithm, reading a graph from a file algorithm. The critical routine is insert edge. We parameterize it with a boolean flag directed to identify whether we need to insert 2 copies of each edge or only one. Note the use of recursion to solve the problem. So we use recursion here. If directed is equal to false, insert edge g y x true. Call the same function recursively. Printing the associated graph is now simply a matter of nested loops. So you use nested loops for I equal to 1, I less than or equal to j n vertices I plus plus, printf %di. For j is equal to 0, j less than g degree I j plus plus, printf %d g edges I j.